So this next reaction that I want to take a look at you with is the reaction with nitrous acid. Well, it turns out that it's a very useful synthetic reaction for multi-step synthesis, but unfortunately nitrous acid is unstable and it needs to be generated within the reaction by a reaction of sodium nitrite and hydrochloric acid. So let's take a look at the reaction down here below. So here we have our electrons swinging around and grabbing a hold of that proton, and then electrons then going and living on the chloride ion to give you sodium chloride. All right, so here is your nitrous acid, and that's what we're going to see reacting down below in this second kind of preliminary step to form something called the nitrosonium ion. Now, as far as our reactions are concerned, you're going to be looking for these conditions above your arrow as an indication that you should continue with this type of reaction. Now, that further reacts, so you have your HO and double bond O, right? And you're in the presence of hydrochloric acid, so you have H plus, right, chloride floating around in solution here. And what happens is that this oxygen grabs a hold of that hydrogen. So that would form HO and double bond O plus here. Right, putting all your lone pairs in there. And what that is a familiar leaving group. So here we have a nice leaving group. So what happens next is that we have a set of electrons from our oxygen swinging down, and then we kick off those electrons to oxygen. That'll give us water, right? And then we're going to get a nitrogen, the lone pair, and 1, 2, 3 bonds down here to oxygen with a formal plus charge on it. And that's resonance stabilized. So we can do this. And that would give us our nitrogen then, right, with a positive charge, and then our oxygen neutral down here at the end. Now this ion is the nitrosonium ion. Many of these are carcinogenic, so they're compounds that need to be treated with care. Now that can react in a variety of ways. So I want to look at this reaction below with you guys here. So let's see how that nitrosonium ion reacts with primary amines. So let's start off over here with an R and H2. So we're going to take that and then we're going to react that with NO plus. So N, double bond O, one pair on just like this, positive charge. So the first step of that reaction is we're going to come over and we're going to grab the nitrogen. All right, what that's going to give us is this structure here with an R. We're going to have our nitrogen, 2 H's, another nitrogen, lone pair on it like this. That'll put a plus charge here. Now we can lose either one of these H's, so we're going to go through and we're going to do that. We're going to do that with water as our base. So we're going to swing around and grab that H, put that lone pair back on your nitrogen. That'll give you an R and the lone pair, and then our N double bond O, just like that. All right. We're not done yet, so we're going to continue this reaction. Before we do, though, let's name this. This thing is called an N-nitrosamine. And these are largely carcinogenic also. So we're going to continue this reaction, though. So we are in the presence of an acid, right? We have H3O plus in here from the nitric acid and water. So we'll grab a proton from this, and we want to protonate the end of this. So we're going to grab an H down here. That'll form an R, N, H, lone pair, double bond O, H, plus. And of course, this now is going to have resonance. So we're going to draw the resonance structure of this, and we're going to start off with a lone pair down here on our nitrogen. So we're going to start off and we're going to do this. That's going to make these swing over to our oxygen down here at the end. So what that's going to give us here is the following structure. So here's your R, nitrogen H, double bond, that'll put a plus charge there now. And then you're going to have a nitrogen right here, right, with a set of lone pairs on it, a single bond down here to oxygen, and an H here, right, with two lone pairs down here at the end. So we'll put brackets around that to distinguish it as being resonance structures. And then we are going to grab a hold of the second H here. So we're going to get that one. We're going to use water to do that. So we're going to come down here below with H2O. Grab that H, and there we have it. So that'll give us an R, N, double bond N, O, H, and then we just need to put in all of our lone pairs to make it look good. And we're not done yet. So the idea now is that we're going to convert this into a good leaving group, and we're going to lose it as water. So to do that, we're going to grab another H plus from our H3O. Right? What that'll give us is an R, N, double bond N, and then an OH2 plus. Right? And at that point in time, what we're going to do is this internal flow of electrons. So we're going to do this, and then we're going to kick off water here. So we're going to get H2O, and then we're going to get an R, nitrogen, 1, 2, 3 bonds, lone pair down here at the end, right? And that'll put a positive charge on the middle nitrogen right here. All right, so what we have here is a good leaving group. The N2 is a good leaving group. So and it doesn't react like this all the time, but in essence, what you're going to get is like an R plus, a good electrophile, and then the nitrogen will leave as nitrogen gas. And that's going to help pull that equilibrium right towards the product side of our reaction. Okay, so let's look at how this might react with a secondary amine. These are called diazonium salts. So secondary amine, well, the reaction is going to be much shorter because you only have one H to lose here. So here's our secondary amine. And then to this, you add your NO plus. So we swing around and we do this. That'll give you your R group, your nitrogen. I'm going to swing that H up. And then we have our nitrogen with our double bonded oxygen, like so, and a plus charge here. So here we only have that H to lose. So that's our next step. So it's the same exact first couple steps as that last mechanism. So it gives you an R, lone pair, R, and then an N double bond O, just like so. So this is, again, this is an N nitrosamine. These are more stable than the compound up above because you don't have H's that can be lost from here. So up above that, the continuation of that reaction is called Tautomerism. Right? So if you look at that reaction up above, you had, where is it? You had two H's to lose. So once you have that nitrosamine, that H here can continue to be lost. This can be used in a couple types of multi-step synthesis type reactions. So kind of the flow here for multi-step might look like this. So you could take, for example, benzene, Right, just doing a little review with you guys here. If we want to nitrate that, then we would add HNO3 and H2SO4. That put a nitro group on there. And remember, there's a reagent that we can use that'll take that nitro group and turn it into an NH2 group. Right, so it's HCl and zinc followed by Na2CO3. Right, so we want to have some type of a base in there, just to deprotonate the fact that you're an acid, right? So that's why the Na2CO3 is there. And then what we can do here is now we can add NaNO2 and HCl, and then that makes that molecule. And then that this is called an arene diazonium salt. So an arene, there's an E missing on that. But anyway, there's a lot of reactions that can take place with this, and I don't want to spend a whole bunch of time going over each one of these, but if we look down below, there's a table that lists all those reactions. So a lot of these are very useful. Some of them are used. For example, number 8, the diazonium coupling, is used sometimes to make dyes. So indicators and dyes that you might use in fabric, for example.